All right, for this logarithmic equation, if I have the natural log of this plus the natural log of this equals the natural log of this, if there's more than one logarithm in the sentence, okay, what we want to try to do here is remedy that. We want to try to get it so that it's not in that form where we have multiple logarithms, if you will. Well, what's going to help us on this is the properties that we learned about yesterday. Okay? Because when we have a logarithm the same base, they're both natural logs, okay, and we have two arguments here, and there's a plus between them, wouldn't that be the same as the natural log of 2x plus 1 times x plus 3? Couldn't I use my product rule? Okay, had that been a subtraction sign, then it would have been the natural log of the quotient of those two. Okay? So we're just changing the form of the left side by using our product rule. And now, take a look. We got natural log of this plus equals the natural log of this. What does that tell us about these two arguments then, if the two natural logs are equal? The two arguments would have to be what? They have to be equal also. Okay. So if we set 2x plus 1 times x plus 3 equal to 8 minus 2x, what we got to recognize here is that we have a quadratic equation here. We should be able to get two solutions out of this then, shouldn't we? Okay. So let's find out if we do 2x squared, if we do the FOIL method here, we're going to get plus 6x plus 1x, that'd be 7x plus 6. And on the right hand side, move this stuff over to the left. We have our 2x squared, and it'll be plus 9x and minus 2. Ash? Yep, sorry. So that makes that negative 5 here then. And of course, once we get that quadratic equation, if we're lucky, it's factorable. If we're not lucky, we'll have to use the quadratic formula to find the two solutions. In this particular case, it is factorable. If we go 2x, and 5, and 1, and x, we get 10 on the outside, 1 on the inside. So however, whatever method you use to factor that, do so. Okay. But ultimately, if we unfoil that, again, we'd have 10, negative 1, that makes the 9, 2x squared, and then negative 5 on the last. Okay. With that said, we'd have 1/2 and negative 5 as our two solutions. Okay. Now, just like any other equation, though, what should we do with those numbers to make sure we're good? Put them in the equation to make sure that checks. Because I can tell you right now, one of these doesn't work. Because if I put negative 5 into this, I'm going to have negative 10 plus 1, that's negative 9. And what about the natural log of negative 9? Okay, that doesn't exist. Okay, remember the natural log, we can only put positive numbers into the logarithms, and therefore negative 5 is out. Okay, so even though we got that, it's an extraneous solution, so we can't use it. And if we try 1/2, however, if I were to put a 1/2 in here, I'd get the ln of 1 plus 1, so I'd get ln 2. So for the check part, I get ln 2 plus 1 in here would give, or 1/2 in here would give me ln of 3.5. And then over here, if I put a half in there, I'd get ln of 8 minus 1, that'd be 7. Okay. And using our properties that we learned about yesterday, if I were to put these two together and multiply the two arguments, wouldn't it be natural log of 2 times 3.5? And what is 2 times 3.5? It's 7. So does it check? Absolutely. Okay, and again, just to illustrate, as we know, if I were to take these two and put the left side in my y1 and the right side in my y2, could I use a graphing approach to find the answer to this also? Absolutely. And we would find that there is only one intersection point at the 1/2. Negative 5 would not be part of it. Negative 5 not even in the domain of these functions. Okay. Well, except for that one. Negative 5 would be okay to put in here, wouldn't it? Okay. So I get 8 plus 10, 18 in there, so that one would give us a valid answer, but these two wouldn't. Questions so far? Okay, now what we're going to finish up with today is we're going to talk about a few applications of exponentials and logarithms that we use in real life. Okay, we've talked a little bit about this topic we're going to get to, but before we talk about the specific examples of where these are used in real life, I want to talk about this idea of orders of magnitude. Okay, we generally say orders of magnitude when things differ by 10, okay, by a multiplier of 10 or 100 or 1,000 or 10,000, etc. Okay, like in the case of, these are just a few examples of things that they differ in order of magnitude. Okay, we say that a kilometer is 3 orders of magnitude longer than a meter. Okay, ultimately because if I have a kilometer, the next smallest is the hectometer, and a decameter, and then a meter. And remember, if a meter is 1, okay, 10 times more than that would be the next one. 100 times more than the meter would be the next one, and then 1,000 times more would be this one. So anything that's 1,000 times more than something else, we say is 3 orders of magnitude larger. Okay? Whereas this one would be how many orders of magnitude larger than the meter? This would be 2, and this one would be 1. So it's all about powers of 10. Okay? However many powers of 10 you are above or below something, okay, is the difference in the order of magnitude. When we have a dollar compared to a penny, a dollar is a penny we'll call 1. Okay, a dime would be 10 pennies, so a dime would be 1 order bigger than, and a dollar would be 100 pennies, right? So if I compare if one is 1 and the other one is 100, this is going to be 2 orders of magnitude bigger. Okay, if I have 8 million people in New York and I have 8 people in Earmuff Junction, okay, so I have 8 people here, 80 would be 1 order bigger, 10 times. 800 would be 2 orders bigger. 8,000 would be 3. 80,000 would be 4. 800,000 would be 5. And then finally 8 million would be how many? 6. Okay, so we'd be 6 orders of magnitude higher if we were 1,000,000 times greater. Okay. All right. So, with that said, we're going to look at, like I said, the applications of logarithms that we see in real life here. First of is the Richter scale. Okay. Notice the equation here involves a logarithm. Okay. And ultimately, any equation that involves a logarithm is going to we're going to be able to talk about this idea of orders of magnitude. Okay. So ultimately, the Richter number that we get on an earthquake is calculated by taking the amplitude, which is measured by a machine, if you will, and the T is again measured by a machine as well, and then B accounts for the weakening of the seismic wave with an increasing distance from the epicenter. Okay, all stuff that can be calculated, that can be recorded with a machine ultimately. Okay, so if we were to be able to come up with those 3 values, that would give us a Richter number for the earthquake. Okay? And ultimately, if we know those numbers, then this is pretty easy to find the Richter number, of course. Okay? But one thing I want to talk about is what's the difference then between an earthquake with a 4 and an earthquake with a 5? Okay? Okay, how much more devastating is an earthquake that's 4 or 5 than the one that's 4? Okay, ultimately, it's all about these orders of magnitude. So every time I go up another Richter number, okay, because of the logarithm here, okay, it goes up by another power of 10. So when I say it goes from 4 to 5, that doesn't sound on paper like that's much different, but it's really 10 times more devastating than the 4. If I went up to a 6, okay, then the 6 is going to be 100 times more devastating than the 4. So every time I go up a number, okay, it doesn't just go up one number, it really goes up by a power of 10. Okay, so what's the difference between a 4 and a 7? 1,000 times more devastating than a 4. So really, is there a big difference between a 4 and a 7? Okay. You know, on paper it looks like it's 3, but really, how much worse is it? It's 1,000 times worse than a 4. Okay. All right. Similarly, in chemistry, we talk about pH, which measures acidity in a solution. It's also based on hydrogen ions concentration. And pH, if we just did the hydrogen ion concentration, we have pretty big numbers. So ultimately, by taking the logarithm, it gets us to numbers that are nicer numbers between generally 1 and 14, we say. Okay, if it's closer to 1, it's more acidic. If it's closer to 14, it's more basic. All right, and so if we take the log of the hydrogen ion concentration of a particular solution, and then we do the opposite of it, we're going to get a number like 3, let's say. Okay. And again, how do 3 and 2 compare? Okay. Well, the order of magnitude going from a 3 to a 2 would be a power of 10 once again. So it would be 10 times more acidic. Okay. 2 would be a 10 times more acidic than 3 would be. Okay. And chemistry people, am I saying that right? Acid is lower, right? Base is higher. Okay. Just make sure. I took chemistry in 1988. Okay. So if I went from a 3 to a 1, okay, that means that that one solution is 100 times more acidic than the 3. Okay, and we could say the same thing going the other way with the basic. Okay. Another application, this one involves an exponential function. This is what we call Newton's law of cooling. And we'll study this again in calculus because there's some calculus repercussions of this. But ultimately, if we have an object, like if we take, say, a hot cup of coffee and we set it outside, okay, it's going to cool according to Newton's law of cooling. Okay? And ultimately, it's going to be dependent on what the temperature was when we put it outside, what the temperature of the outside is, okay, and then also some constant K that we use. And once again, as long as we know the values of these things, then it's pretty easy to compute. Okay, we just plug them in and do the math. It's not difficult to compute. But this is just another example of something in real life that relies on exponential functions. Okay. We will do. I do want to do one problem using Newton's law of cooling. Okay. So we have a hard-boiled egg, comes out at 100 degrees Celsius, placed on in a 15-degree water to cool. 5 minutes later, the temperature of the egg is 55, and the question is, when will the egg be 25? Now, if we fill in the blanks on the formula, let's just see what that's going to look like. Okay. Okay. So over here on the left-hand side, if we fill in the blanks, okay, the temperature, the 55, is what we want the egg, or what the egg was 5 minutes later. Okay, this was the T sub 0. This is the surrounding temperature that we put it in, or T sub m, I should say. T sub 0 is the initial temperature, okay, and then the time here is 5. Okay, the problem that we have here with going right to the answer of when will it be 25 is we don't know K. They didn't tell us what K equals. So if we were just to figure out the time, which is this variable, we would have two variables over here. We'd have K and little t. Okay. So by telling us this information that 5 minutes later it got down to 55, okay, that allows us to find K. Okay. So to do that, just like we solved earlier when we solved our exponential equation, we got the e to the k part alone, and then we took the natural log of both sides, and then we divided by, in this case, we divide by 5 to get k alone, okay, and that right there would be our k value. So they estimated the k to be 0.1507. Okay. So with that said, now we can rewrite the equation, start over again. Okay, this is the technique here. And we're going to put the other numbers in there. Now we want to know when it goes from 85 to 25 in a 15-degree situation. And this time we know K, so the variable we're going to find is T. So the solving part is going to be exactly the same as what we just did. We'll get the E part alone. Okay. And then we'll take the natural log of both sides. And then from there we'll divide by the negative 1.507. And we get an answer of 14.2 minutes. Okay. And of course we would round that to the nearest third decimal place instead of the first. Right? Okay. Any questions on that technique? So again, basically with the information you're given, fill in the blanks and find K. Once you know K, then you can refill in the blanks with the new information that you're after and solve that sentence the same way. So you're really doing that same solving process twice. Okay, so for our work today, we're primarily working on equation solving using the techniques that we learned about. Okay, and then in the second part of that assignment, we're going to be working with some of those equations that we just talked about, using logarithms and exponentials in real life situations, especially with the Richter scale, pH, and Newton's law of cooling. Okay.